Now discussing about the second order system, and yesterday we have derived all the time domain specifications of the second order system, and we have seen one numerical problems also, right? So now we will continue with the thing is given a feedback system. This is the output y of s, input e of s, this plus. It is a negative unity feedback system, and the forward gain is, path gain is 4 divided by s multiplied by s plus 4. Okay. Question is find the peak overshoot of the system to a step input. So how will you find this? First of all, you have to convert this block diagram to a single transfer function. So since it is a negative feedback system, you can directly convert like this: y of s by u of s is equal to g of s divided by 1 plus g of s h of s, right? So this is g of s by s plus 4 divided by 4 divided by s plus 4. Finally, we get 4 divided by a square plus 4s plus 4. Right? So this is a second order system. If you compare with standard transfer function of the second order system, is a square plus 2 zeta omega n plus omega n square. Right? So in order to find find the peak overshoot, you need zeta, right? So what is the zeta if you compare both? Theta is 1. Okay, fine. That means omega n is equal to root 4, which is equal to 2 rats per second. 2 zeta omega n is equal to 4. That means zeta is equal to 4 by 4 is equal to 1. Okay. So zeta is 4 means this is which kind of system? We already studied, right? It's a critically damped system. When zeta is 1, we can call that system as critically damped second order system. Okay. Now find the peak overshoot. What is the formula for finding that in terms of zeta? Peak overshoot in percentage is equal to e power minus zeta pi by root of 1 minus zeta square. So what will be the value if you substitute 1? What is the value you are getting? Infinity. Yeah. The e power infinity will come, right? Yeah, that means percentage is 0. Right? So how will you draw the output response for a critical damped system? For an undamped system, there will be some oscillations and finally it is settling, right? So if we draw the response with respect to time, how the waveform looks like. Yeah. That I will give as homework. You can derive the step response of the second order system for a critically damped system, right? So if zeta is equal to 1, the transfer function becomes omega n square divided by x square plus 2 omega n s plus omega n square, right? That becomes omega n square divided by s plus omega n the whole square. So you do the analysis and see. But from this, you can understand that there is no overshoot, right? So that means the response will be like this. It is reaching the steady state without any oscillations, because our percentage MP is 0 in this case. Anyway, you derive the step response for this particular system and see whether it is coming correct or not. Right? In this case, we are having 2 poles, which is at minus omega n. Right? Okay. Now, we take one more system. This is the block diagram of the system. Note down this. There is also a negative feedback system. This is E of s, and this is 4 by s square. This is also a negative feedback system with the unity feedback. Now, do the same analysis. Find the peak overshoot. There is a question. Because I want to tell some thing. That's why we are repeatedly doing this. Okay. So for this system, first of all, you have to derive the transfer function. So y of s by u of s becomes 4 by s square divided by 1 plus 4 by a square. That is 4 divided by a square plus 4. Right? So in this case, what is the value of zeta and omega n? Omega n remains the same.
Omega n equals to 2.
Yeah. Like previous case, yeah, zeta is 0, right? That is the observation. Zeta is 0. So zeta is 0 means it is a undamped system, right? Yeah, undamped system. What about the system poles in this case? We already mentioned that for an undamped system, poles will be purely imaginary. Yeah, correct. So in this case, it is plus or minus 2, J2, right? And if the poles are at exactly at imaginary axis, what is the natural frequency of oscillation? This also we have seen, right? It is equal to the pole. So the natural frequency of oscillation is 2 radians per second. Right? So if we draw it in the S-plane, imaginary, real, our 2 poles will be at, one is at plus J2, one is at minus J2. Okay. Now, what is the output response? That is very important. So first we will calculate the overshoot. The question is to calculate overshoot, right? So if you substitute in that equation, what is the value you'll get?
1, sir.
Yeah. That means the percentage of overshoot is 100%. Right? Previously it is 0%. There is no oscillation. For an undamped system, it is 100%. So, what will be the response? We'll see. We know Ts is equal to omega n square divided by s plus omega n sorry, s square plus omega s square, right? In this case, yeah. So if you find the step response, can you find out the step response for this one? That means u of s equal to 1 by s. So t of s becomes, or y of s becomes 1 by s omega n square divided by s square plus omega n square, right? So if you can apply partial fraction, so this becomes a by s plus bs plus c divided by s square plus omega n square. Can you please find the magnitude of a, b, and c and tell me? So, what is the value? Yeah, c equal to 0. Okay, fine. So we can write y of s is equal to 1 by s minus s divided by s square plus omega square, right? So from this y of t, if you take the L inverse, we can obtain the unit step response. So y of t becomes 1 minus cos omega nt. Right. This is the output response of a which system? Undamped system, correct? So what is what will be the shape of this waveform? This is the output is only having sinusoidal time. There is no exponential time, right? So how can we draw? If you substitute t equal to 0, it will start from 0, 1. But at if we draw like this, it will be continuously oscillating, right? Because you already got, for this kind of system, the overshoot is 100%. It will oscillate like that. This kind of system will never settle. Okay, so practically there will be some, indirectly it is telling there is no damping, sorry, there is no dissipating element in this system, right? Dissipating element means this energy will be stored or dissipated somewhere, and it will go to some value, right? But in this kind of system, there is no dissipative element. That's why it is oscillating. Okay. Anyway, we will take one circuit, and we'll see all those things in detail. So this will be the response. So if we conclude, if we draw all the response in single graph, how can we conclude it? So with respect to zeta, the shape of the, means the dynamic of the system, second order system is changing. Let it be y of t. So I have 2, 1. So for an underdamped system, what will happen? It will be in oscillating stage. This is for underdamped system. And finally, it will settle in a band. Okay. Now, for undamped system, peak will be, just change here. Will be purely sinusoidal and oscillating in nature. Right? It will never settle. This is for zeta equal to 0, and the first one was for zeta is this one. This one, zeta is less than 1, right? Now, what about zeta equal to 1? It is a critically damped system, and we have seen that there is no steady state oscillation, there is no overshoot. It will gradually increase and it will settle. So this will be for zeta equal to 1. So now can you tell what is the response you are expecting for zeta greater than 1? Can you tell? That also you do as homework. You calculate the step response for the overdamped system also. So overdamped in the sense the waveform looks like for an overdamped system also there won't be any oscillations and overshoot. But what is the difference between these two? Zeta equal to 1 and this one. Yeah, correct. So critically damped is the faster one compared to overdamped system. So if zeta is greater than 1, one thing you can observe that there is no oscillations in the output response, there is no overshoot, but it is reaching the steady state after some time. So if you increase zeta, the curve will move right. So the conclusion, we will summarize the study. For a second order system, the output response of the system greatly depends upon the damping factor of the system. So if it is 0, it is purely oscillating, there is no dissipative element. If it is zeta is less than 1, and the output response consists of exponential time multiplied with sinusoidal time. So it will start with some oscillation and it will settle after some time. When zeta is equal to 1, there is no imaginary poles exist in the system and there is no oscillations also. It will reach the steady state faster. But when zeta is greater than 1, in that case also there is no oscillations as well as overshoot, but it will take some time to reach the steady state. So the response is changing with respect to different system. Now, different zeta value. Now we will take one electrical circuit, second order electrical circuit. So we already seen first order system, right? Can you tell one example for electrical circuit, first order electrical circuit? RL circuit, right? Okay. Now you take one electrical circuit like this. R will be there. L, C. Let this piece be of T. R, L, C, and let I of T the current flowing through this, and output voltage is the voltage across the capacitor, V out of T. Now we have to find the transfer function. This, let it be, this one is Vi of T. We need to derive the transfer function V of S divided by V out. This is our A. Okay, now we'll start. One way of doing is, as we studied in unit first, you just apply the Kirchhoff voltage law, then apply Laplace transform. Otherwise, what you have to do is you directly write the impedance of each element, right? Okay, now anyway, I will write the Kvl equation. So Kvl equation becomes V of T is equal to R I of T plus L d I of T divided by dt plus 1 by C integral V of T dt. Right? So if we apply Laplace transform, you will get Vi of S is equal to R plus SL plus 1 by SC multiplied by I of S. So I of S can be written as VI of S by R plus SL plus 1 by SC, right? But our aim is to find V I of S by V out of S. Sorry, V out of S divided by Vi of S, right? So how will you find the output voltage? Output voltage is nothing is 1 by C integral I of t dt. So in S domain we can write Vi of S is equal to 1 by SC I of S. You already know I of what is I of S. Substitute here. Then the equation becomes Vi of S divided by SC multiplied by R plus SL plus 1 by LC, right? So rearranging this, we can find out the transfer function. So transfer function is nothing but V out of S divided by Vi of S. So if you move to this side, what will happen? How can we write this equation? It becomes yes. SC R plus plus. Oh, I really have to multiply right here. I think I made some mistake somewhere. This is SC, right? Yeah, that's it. Becomes SCR plus S square LC plus 1 divided by SC. So this will cancel. So if I can be written as 1 by LC S square plus S square plus R by L S plus 1 by C. Right? So this is a second order system. So if you compare the polynomial, denominator polynomial with the standard equation, one thing you will get is omega n is equal to root 1 by LC, Rads percentage. What about zeta? 2 zeta omega n is equal to R by L of zeta becomes R by 2L by zeta. So zeta is under root LC, so we have root LC and we can write L R by 2 root C by L. Clear? So this will be the zeta of the second order system. So for an RLC circuit, omega n square is 1 by root LC, right? If you know the value of L and C, you can find out omega n. So the nature of frequency of oscillation depends upon the energy storage elements. And what about zeta? So damping depends upon all the factors R by 2 into root C by L. And one more observation is there. Previously, there's only one energy storage element, right? RL This is a dissipate element. This is an energy storage element, right? In this case, what is the order of the system? 1. Now we added one more energy storage element, right? In this circuit, R is the dissipative element, L and C are the energy storage elements. So what is the order of the system? 2. So what do you observe from this? Right. The order of the system is equal to number of energy storage elements. Clear? So suppose one more L is connected in parallel with this, it becomes third order. That is the meaning. Okay. Clear? Okay. Right. Now, the same circuit you do one small change. You remove R. You remove the dissipating element. You keep only energy storage devices. Let it be the same. V of t, L, C, I of t. Find the transfer function for this. Can you find the transfer function for that? Yeah, I'll do and tell me. What is the transfer function? So you are telling V out by VI of S, right? 1 by SL plus SL. Okay. So this will cancel. I will get S square LC plus 1. So it can be written as 1 by LC divided by S square plus 1 by LC. Right? 1 by LC divided by S square plus 1 by LC the whole square. Right, now we need to move. So in this system, what you observe, since R is not there, what is the theta?
Theta equals to 0.
0. So this is an undamped system, right? Already we have derived the standard form of the undamped system, right? So what is the transfer function of the undamped system? It is omega n square divided by S square plus omega n square. And you for an LC circuit, you got the transfer function as 1 by 1 by LC divided by x square plus 1 by root LC the whole square. Correct? So if you compare both, what is the omega n? Yeah. So our natural frequency of oscillation remains same. Omega equal to 1 by root LC. And what is the response of the system? For an undamped system, we have derived that it is 1 minus cos omega nt, right? So in this case, it becomes 1 minus cos 1 by root LC into T. So what will be the response of the current? Current or voltage across the capacitor? Hmm? Hope you understand why it is oscillating. Why it is oscillating? Because yeah, means here there is no energy dissipating element, right? First, inductor will store some energy. After some time, this energy stored in the inductor will be transferred to capacitor. Again, after some time, capacitor will transfer this energy to inductor. So there is no dissipating element, and it will be in oscillating stage. If you add some dissipating element, the energy will be dissipating in the element, and finally it will go to settle at some point. That is the meaning. Clear? This is under the response of the RL circuit. Sorry, LC circuit. See, suppose I want to find the current response in this. Current in the sense I of t. What the waveform you are expecting? Now we have drawn the voltage across the capacitor, right? I want to find the current through the inductor. You can do it, but you will get the same result only. It will be in oscillating only, right? Anyway, you do the analysis and check whether it is like that or not. Okay. So now the section. Okay. What is this problem? I have a system block diagram like this. This is E of S plus forward path going K divided by S multiplied by S plus 2. This is output. It is not a unity feedback system. There is a mapping between the output and feedback signal. And that mapping is 1 plus AS. This is minus. We are feeding this to you. Okay, now the question is given the damping ratio of the system is 0.7 and natural frequency of oscillation is 4 radians per second. So we have to find what is the value of K and K. Can you do it? Zeta is given, omega n is given. Find the value of constant K and A. Do and tell me. First of all, you convert this plot diagram to a single transfer function and compare with standard second order system. And the zeta is 0.7, so that means the given system is an underdamped system. Okay, can you do it? Yeah.
Sir, K equals to 2 and A equals to 1.8, sir.
K equal to 2. A equal to how much?
1.8, sir.
I think you might have done some mistake. Once again, check it. Yeah, that's what. K equal to 16. A equal to? I think this you check it once. This is wrong, I think. You made some mistake somewhere. This is correct. K equal to 16 is correct. Anyway, we'll do it and see. First of all, you obtain your transfer function of the system. Now, if I solve this, I get K divided by A square plus 2S plus K plus AKS, right? So this can be written as K divided by A square plus 2 plus AK plus SK. So omega n is not given. Yes, n is given, right, in the question. Omega n is given 4 radians specifically. Now this you can compare with the standard form. So you can get omega n is equal to root k, right? Given omega n equal to 4 radians per second, so root k equal to 4, if square of both sides, we will get k as 16 radians per second, right? How will you find a? So that you have to compare the second term, 2 zeta omega n equal to 2 plus ak. So zeta equal to 2 plus ak divided by 2 omega n. So 2 into omega n is 4. Solve this and tell me what how much it is coming. And given zeta is equal to 0.7, right? Our aim is to find a. Yeah. It can be written like this. 0.7 into 8, right? 0.7 into 8 into 2 plus 16a. Here becomes how much it is correct? 0.225. Yeah, it is correct. So these are the k equal to this one, k equal to this one. Okay, fine. So this kind of questions we can expect in GATE exam. Okay. We'll solve one more problem and wind up. Okay, tomorrow we will start new topic. Mechanical system. You can refer control system engineering by Norman S. Weiss. A lot of problems are there in this book. You can go through it right here. Control systems engineering. By Norman S. Weiss. A lot of numeric examples are given in this. Now, one more problem will be 5 more minutes in correct? Yeah, not on this. We will do in one mechanical system, rotational mechanical system. Okay. So we will not on this. My husband. What's the first element? And one dashboard. Going to the reference point. Now, I think we have done only for translational motion, right? For rotational motion, we have not done any problem. Okay. Anyway, it is similar to translational system only. Only difference is instead of force, torque will come. Instead of displacement, angular displacement will come. Velocity, instead of velocity, angular velocity will come, right? Suppose the rotation torque is Ti. It will be T of T. Angular displacement is theta of T. J is the moment of inertia, K is the spring constant, and B is the viscous coefficient. Okay. The question is, find the value of J and D of the system to yield 20% overshoot and a settling time of 2 seconds for a step input of torque. Do you have next hour class? Okay. Anyway, now we can try. Need 2 more minutes. The question is, we want to find out the value of J and D in such a way that the overshoot in the response is 20% and the system have a settling time of 2 seconds for a step input of torque. Okay. Given K is equal to one more parameter we required right, for this calculating this. K is equal to 5 Newton meter per radian seconds. 5 Newton meter per radian second. Okay. So for that, first of all, you want to find out the transfer function. So how will you derive the transfer function for this? Like in mass system, you can apply the concept here. So in terms of theta, you have to derive, right? So the applied input is T of S is equal to torque due to this inertia element. How we can write? Moment of inertia into d square theta by theta square. There you have written that m into dx square by dt square. Sorry, dt square, right? Plus b, because both are connected to reference point only. So there is no difference in torque, right? So this becomes d theta by theta plus k theta. So if you apply Laplace transform. You can find the transfer function. What is the value? Okay, we will continue tomorrow. Anyway, you do the exercise. Already you know the concept, right? We will see the answer tomorrow. So if you have any doubt, please ask. Otherwise, we can write up the meeting.